Bismillahirrahmanirrahim. In the name of Allah, who is the most merciful and most beneficial God. Assalamu alaikum. My name is Iman Sarfraz and my department is BS Biotechnology, third semester, and my ID password is 220132310006. Today my presentation topic is what are MOR materials, microporous and mesoporous materials. The contents of my topic are introduction of MOR materials, mesoporous and microporous materials, size of the pores, synthesis methods, hard template method, sol gel synthesis method, hydrothermal synthesis method, structural properties of MOR materials, applications of MOR materials, X-ray diffraction, gas absorption, scanning electron microscopy, transmission electron microscopy, applications in industry and research, drug delivery, catalysis, adsorbents, chromatography, and conclusion. So first, introduction. What are MOR materials? The modulus of rupture of the material is defined as the maximum bending stress that can be applied to that material before it yields. MOR is the strength of a material as determined by flexural or torsional test. It is a measure of specimen strength before rupture. Microporous and mesoporous materials. Microporous materials have pore diameters of less than 2 nanometer. Mesoporous materials have pore diameters in between 2 nanometer and 50 nanometer. Mesoporous materials are better than microporous materials for the excess diffusion of larger molecules, but also for the immobilization of metal complexes or for reacting two or more molecules. Mesoporous materials have properties including ultra-high surface areas and large pore volumes, tunable pore sizes and shapes, and also exhibit nanoscale effects in their mesochannels and on their pore walls. Here is showing the sizes of the pores. So first, microporous materials is the size of less than 2 nanometer, and mesoporous materials size is between 2 to 50 nanometer, and macroporous materials size is greater than 50 nanometer. Synthesis methods of MOR materials. There exist various strategies of mesoporous material synthesis. Most of them are based on the use of organic template molecules as structure directing agents around which the precursor condenses. It is so-called soft templating method. In this approach, after the mesophase formation, the organic template is removed by calcination or extraction. The removal of template results in the generation of ordered mesoporous structures whose mesopore sizes can be tuned using different surfactants as the template. Next, hard template method. This strategy is commonly applied in the synthesis of mesoporous carbons. In this technique, the mesoporous template is loaded with organic materials, for example, sucrose, and the organic filler is carbonized in the vacuum. Dissolution of silica shell by sodium hydroxide and hydrofluoric acid results in uncovering of carbon framework. In the group of hard templating methods, double replication procedure can be distinguished. In this preparation technique, mesostructured silica can be used as a template for mesoporous carbon and this hard carbon matrix, and this serves as a replication matrix for Mesoporous metal oxide. Here is showing the picture of hard template method. The template components are surfactants, emulsions, co-solvents, swelling agents, and the medium is acidic or alkaline. Matrices precursors are alkoxysilanes, metal oxides, metal oxides. Next, sol gel synthesis method. The sol gel process is a more chemical method, but chemical method for the synthesis of various nanostructures, especially metal oxide nanoparticles. In this method, the molecular precursor, usually metal oxide, is dissolved in water or alcohol and converted to gel by heating and stirring by hydrolysis, alcoholysis. The gel obtained from hydrolysis alcoholysis method is wet or damp. It should be dried using appropriate methods depending on the desired properties and application of the gel. For example, if it is an alcoholic solution, the drying process is done by burning alcohol. After the drying stage, the produced gels are powdered and then calcined. The sol gel method can be used in the process of making ceramics. Here is showing the structure of precursor plus solvents, soil formation, colloidal structure in soil, next connected pore structure gel. Step 1 is hydrolysis, step 2 condensation take place, and in step 3 and 4 aging and drying, and step 5 calcination, and final product is formed. Hydrothermal synthesis method. It involves performing a heterogeneous reaction in an aqueous medium at temperature above 100 degrees Celsius and pressure above 1 bar. Hydrothermal synthesis is the most suitable route for the preparation of zeolites and other related mesoporous structures with engineered pores. Hydrothermal synthesis has emerged as a preferred route for the synthesis of metal oxide nanoparticles. Materials which have high vapor pressure near their melting points can be grown by the hydrothermal method. This method includes the need of expensive autoclaves and the impossibility of observing the crystal as it grows if a steel tube is used. There are autoclaves made out of thick walled glass which can be used up to 300 degrees Celsius and 10 bar. Next, here is showing the structural properties of mesoporous materials. Ordered mesoporous materials can be classified according to their structure dimension and pore geometry. Example, either 3D, 2D or 3D, cylindrical or 3D, cage type structures such as MCM48, AMS6 lead, MCM41, SBA15 and NFM1 P6 millimeter possesses uniform pore diameter and show potential towards applications in catalysis, adsorption, and drug delivery vehicles. In contrast, cage-type mesocage solids such as FDO1, SBA1, PMN, and AMS8 FDM consist of spherical or ellipsoid cages that are connected three-dimensionally by smaller cage connecting windows, which could be used to control the mass transfer of active agents. Next, the structure MCM41, second one is MCM48, and the third one is MCM50. 2D versus 3D. MCM41 2D hexagonal P6mm unidimensional pore system, and MCM48 3D cubic interwoven and continuous 3D pore system. Applications of MOR materials. X-ray diffraction. X-ray diffraction is commonly used to identify the crystallographic symmetry of material phases at both the nano and mesoscale. Phase identification for mesoporous materials can be difficult because most of the peaks appear at low angles and may overlap because of similar short range. X-ray diffraction is a powerful non-destructive technique for characterizing crystalline materials. It provides information on structures, phases, preferred crystal orientations, texture, and other structural parameters such as average grain size, crystallinity, strain, and crystal defects. Here is showing the structure of X-ray diffraction. Gas adsorption. Gas adsorption is a complementary method used to obtain a comprehensive characterization of porous materials. Adsorption of gases at various relative pressures on the porous solids provide information about properties including surface area, pore volume, and pore size. The adsorption of the gas depends on the nature of the adsorbent, factors affecting the extent of adsorption. The extent to which adsorption will happen on a solid surface depends on the following factors, such as surface area, nature of the gas, exothermic nature, and pressure. Here is showing the structure. So the first picture is absorption, and the next is showing the adsorption. Scanning electron microscopy. Scanning electron microscopy is a test process that scans a sample with an electron beam to produce a magnified image for analysis. Scanning electron microscopy utilizes a high beam of electrons to image the surface of nanomaterials. For scanning electron microscopy, clear magnified images with higher resolutions are created by electrons as opposed to the use of the light waves by conventional optical microscopes. It is a technique where only milligram quantities of materials may be used to determine the particle size, shape, and texture. It is a technique to image surface morphology by providing information about size, shape, and morphology of the samples. The surface morphology of nanoparticles can be examined by scanning electron microscopy because it detects the scattered electrons from the particle surface. Scanning electron microscopy usually use acceleration voltage of 30 kilowatt. Here is showing the picture of scanning electron microscopy. Transmission electron microscopy. Transmission electron microscopy is an analytical technique used to visualize the smallest structures in matter. Transmission electron microscopy can reveal the stunning detail at the atomic scale by magnifying nanometer structures up to 50 million times. It is a quantitative method to determine the particle size, shape, and distribution. It is one of the most suitable techniques available to analyze the morphological properties of a single nanomaterial. It is a very powerful microscope with high magnification resolution. Transmission electron microscopy at present provides a resolving power of about zero point 0.2 nanometer. Transmission electron microscopy usually use acceleration voltages up to 60 to 300 kilowatt. Here is showing the picture of transmission electron microscopy. So the first picture size is 20 nanometer, and second one is also 20 nanometer, and the third picture the size of particles is 50 nanometer, and in the last one the size of particles is 100 nanometer. Applications of MOR materials in industry and research. Drug delivery. Mesoporous silica nanoparticles are widely used as a promising candidate for drug delivery applications due to silica's favorable biocompatibility, thermal stability, and chemical properties. Silica's unique mesoporous structure allows for effective drug loading and controlled release at the target site. Mesoporous materials which have unique pore size, high surface area, and pore volume have been widely employed as carriers for controlled drug delivery. Compared with amorphous colloidal and porous silica, mesoporous silicas exhibit higher loading of drugs and provide a controlled drug release if modified by functionalization. So the next, catalysis. In catalysis, high surface area materials with nanoscale features are used to develop highly selective catalysts that reduce energy use and waste pollutant generation in industrial applications. Porous materials such as zeolites, microporous solids are widely used in industry as catalyst and catalyst ports. However, when large molecules are involved in a catalyzed reaction, mass transfer limits the suitability of zeolite structures. Attempts to improve the diffusion of reactants to catalytic sites have been resolved by enlarging pore sizes to the mesorange. These ultra selective catalysts can cut costs significantly in many industries. Absorbents. The high surface area of nanoporous materials allows their use as absorbents for various gases, liquids, and toxic heavy metals. The uptake of these substances can be increased significantly based on the surface properties, hydrophobicity, hydrophilicity, and functionality of the mesoporous silica materials. Several applications, such as the removal of pollutants from water, storage of gases, for example, CO2, H2, O2, CH4, and H2S, absorptive xylene separation, and separation of biological and pharmaceutical compounds have been addressed through the use of mesoporous materials as absorbents. So, the next, chromatography. The large pore volume, surface area, and narrow pore size distribution of mesoporous silica makes it a good candidate for size exclusion chromatography. These materials have been proposed as ports or stationary phases for size exclusion chromatography, capillary gas chromatography, proteomics separations, normal phase, high pressure liquid chromatography, as well as enantioselective chromatography. So the last one is conclusion. Mesoporous materials have witnessed a great progress over the past decade. The potential applications of functional mesoporous materials in adsorption, separation, catalysis have been discussed, which gives the useful principles of the structure property performance relationships. The properties of mesoporous and microporous membranes are determined by pore size, porosity, and membrane thickness. Significantly, the mass fabrication of functional mesoporous materials with diverse compositions and structures are of great importance. Fully understanding the formation mechanism and intelligent synthesis of mesoporous nanostructures will obviously benefit the research and further applications. Thank you.